Hello students, it's Dr. Mick again, and welcome to the lecture on Chapter 7. Actually, this is lecture 1 of 2 for Chapter 7. In this lecture, we will introduce arrays, very important programming construct. That will be section 7.1, and then we will cover Chapter 7, Section 2, arrays as used in functions. And that will be the extent of this lecture. And then next week, which will be the final content presented in this class, we will cover programming with arrays, Section 7.3, and finally multidimensional arrays. And that will be the end of the content for this course. So let's get started on 7.1, Introduction to Arrays. Section 7.1 will introduce the concept of an array, which is a collection of items that is stored and referenced as one variable location. Let's drill down on this topic now. As I alluded to in the previous slide, an array is used to hold and process a collection of data of the same type. An example that the author gives here is a list of names or a list of temperatures for a specific city. Imagine keeping track of 100, 1,000 test scores in memory. How would you name all the individual variables to hold the test scores? How would you process each of the variables? You could simply have an index, students 0 through 500, and store their names in indexed locations in a single variable. Let's take a closer look. Here we're going to explore declaring an array. And the array will be named score, and it will hold 5 variables. Each of the variables stored in the array will be an integer. So we declare this as, just like we're declaring an int, score, and then in the brackets, the number of integers that will be stored or referenced by this array. So, and it's a zero-based indexing system, which means you're declaring 5 variables, 5 integer variables, and they are stored or indexed as 0 through 4. It's an n-1 zero-based index system. The value in the brackets is called the index. Also, I've heard it called the subscript, but we're going to call it an index. And it's how we reference each of the integers in this integer array. I think I mentioned this in the previous slide. The variables in the array are referred to as indexed variables or subscripted variables, or also called elements of the array. And the number of indexed variables in an array is the declared size of the array. The largest index is 1 less than the size. Remember, it's zero-based indexing system. So if you have an array declared as a size 10, it holds 10 indexed variables, but it's 0 through 9. Any variable type that we've already introduced can be used in an array. An array can have indexed variables of any type: ints, doubles, floats, chars, bools, etc. But all the index variables in an array must be the same type. You can't have a mixture of variable types. And this is also referred to as the base type of the array. An indexed variable can be used anywhere an ordinary variable of the base type is used. It just has to be referenced with its index, and we'll see that in slides coming up. We use brackets to enclose the size of the array. Here's a declared array. Its name is score, its base type is integer, and it holds 5 integers, so its size is 5. When we refer to one of the index variables, the brackets enclose a number identifying its index. For example, score and then a 3 within brackets is one of the indexed variables. At index location 3, there is a value stored, and it can be any expression that evaluates to one of the integers 0 through size -1. So you could use a counter in there, or a variable that is used as a counter. In other words, the index can be referenced by an expression, and we'll see that moving forward. And as you might have guessed, you use the assignment operator to assign a value to an indexed variable or to initialize it. So here we have, we're declaring an int, a regular int, n, and we're initializing it to 2. And we are then taking score index n plus 1, which resolves to 3. So index location number 3 is assigned the value 99. Take a look at that for a second. Sometimes the first time you see this, first time students see this, it can be a little perplexing. So let's just pause for a second and take a close look at this and make sure you understand how that index is resolved, and that it can be a numeric value or any expression that resolves to one of the index locations. And in this case, n plus 1 resolves to 3. As you might have guessed, we use loops to step through arrays. It's a very common practice. So here's an example of a for loop that is used to step through an array, and it will simply display the difference between each score stored in an index location and the maximum score stored in an array. So in this particular case, the first index is 0 and the last index is size -1. So I'm assuming this is an array that has a size of 6. Here we have a coded solution from your textbook. It's program 7.1, and it actually uses 2 for loops to step through an array. So we've declared an array size 5, which means it has index variables 0 through 5. It stores integers, by the way. And the first for loop is used to determine the maximum score. So this is holding 5 scores. And we use a for loop to step through the array, the index locations in the array, and find the max score. And then the second for loop is used to output the scores and their differences from the highest. Take a close look at this. If this is a hybrid or traditional class, we'll be downloading this code in class and running it, and you have access to this code in the timeline, so take a look at it. It's a common practice to use constants to declare the size of an array. If you use a constant, it allows your code to easily be changed for use on an array or a data set that is larger or smaller. So in this example, we declare a constant int, number of students, and it's set to 50, so that cannot be changed outside of that line being edited. Int score, number of students, so we're declaring an array that will hold the score for a number of students, and the initial case is 50. And then we're using a for loop to step through and whatever. And only the valuable, in order to use this code for a different number of students, a different set of students, maybe 100, maybe 75, maybe 25, only the value of the constant must be changed to make this code work for a different data set size. Take a close look at this. Very useful practice. You must use a constant or a hard-coded number to declare the size of an array. Most compilers, including the compiler we're using, do not allow us to use a variable to declare the size of an array. It needs to set up those memory locations. It needs to know it needs to quantify the exact size. If it's 10 ints, it'll set up memory to store 10 ints. If it's 10 doubles, etc., it will need that size. This slide shows us the syntax for declaring an array, type name, the array name, and the declared size. We've been flirting with this for the past few slides. Should come as no surprise to you. The type name can be any type variable, and the declared size can be a constant or a hard-coded number. It cannot be a variable. And once declared, the array consists of the index variables, the array name, index 0 to the declared size -1. In memory, in computer memory, we have numbered locations called bytes, and a byte's number is its address. So a simple variable is stored in consecutive bytes. The number of bytes depends on the variable's type. The variable's type, each variable type has a different size. We went over that in Chapter 1. A variable address is the address of its first byte. So if a variable takes up 4 bytes, the address is byte number 1. So declaring the array int A with 6 index locations reserves memory for 6 variables of type int. Each int requires 4 bytes, so this will reserve a contiguous 24 bytes of memory. The variables are stored one after another sequentially, and the address of A index 0 or A sub 0 is remembered as the address of that integer array. This slide shows you how an integer array with 6 index locations, or 6 indexed integers, would be stored in memory, and the address of A sub 0 is also the address of the entire array. A very common error is an array index that is out of range. Index values for an integer array size 6 are 0 through 5. Any indexed value not allowed by the array declaration is considered out of range. So if you try to get to index location 6, because remember it's a 0-based index, it starts at 0, runs to n-1, which is 5. This typically does not produce an error message, which is problematic. It will read garbage in the next location outside of the range of that variable. Here's an example of an out-of-range problem. We declare an array of ints, size is 6, and an integer is declared as int I equals 7. And then we execute the statement a sub I, meaning a index location 7 equals 238. So we're trying to assign 238 to an index location for that integer array that is out of range. So the computer will calculate the address of the illegal a sub 7. This address could be somewhere that some other variable is stored. The value of 238 is stored at the address calculated for a sub 7, but no warning is given. This is a problem. This slide shows two ways to initialize an array after it's been declared. The values for the index variables can be enclosed in braces and separated by columns. And there's an example of an integer array named children that has 3 index values, and they're all being initialized on that one line of code. And that's equivalent to initializing each indexed variable with an assignment statement and a separate line of code, as is shown at the bottom of this slide. If too few values are listed in an initialization statement, the values that are listed are used to initialize the first of the index variables. And here's an example where an integer array of size 10 is initialized to 5, 5 in brackets, and that only initializes index 0 to 5 and index 1 to 1, and 2 through 9 will be indexed to 0. This is I guess a warning. If no values are listed in the array declaration, some compilers, key statement there, some compilers will initialize each variable to a 0 of the base type, 0 int, 0 double. However, don't depend on this, and I can't recall offhand what the Visual C++ compiler does in this scenario. Remind me and we'll check it out in class. That concludes section 7.1, Introduction to Arrays. Here are some things for you to consider. Can you describe the difference between a sub 4 and int a sub 5? Sure. One is referencing a variable stored at index location 4 for what I'm assuming is an already declared array. It must already be declared array. And the other is a declaration statement. And then show the output for the for statement, just stepping through index 0, 1, and 2 for a character array, an array of chars that's size 3. The next section is 7.2, where we will explore the use of arrays in functions and how they are called and how they are passed. Stay tuned. Indexed variables can be arguments to functions. Here's an example. We are declaring an int I, an int n, and an array of ints a sub 10, and void my function that requires an int n. Variables a through 9 are of type int, making these calls legal. So you can call my function with a sub 0, or a sub 3, or a sub I. Wherever you need an int or require an int, you can pass one of the index integer variables. Let's take a look at display 7.3 for more details. Here we have program 7.3 from your textbook, in which we have a program that stores the number of vacation days for each employee in index variable locations in an array. And obviously they're ints, because you get 1 day or 2 days. You don't get 3.5 days. Well, not in this company you don't. So If you look, the program uses a for loop to step through the array of vacation days, and for each indexed location, it calls the function adjustDays, and it passes the indexed location, the indexed variable, vacation number. And this function adjustDays simply adds 5 days, 5 employee days, or 5 vacation days to each employee. Take a close look at this. A formal parameter in a function may contain an entire array. And this type of parameter is called an array parameter. It's definitely not a call by value parameter. It's not exactly a call by reference parameter, but it behaves much more like a call by reference parameter does. Let's take a closer look. To specify an array parameter in a function declaration, you use empty brackets in the parameter list. And here's an example of a void function. Name is fill_up, and it has 2 parameters, 2 arguments that are passed to it. The first is an integer array, and the second is an int indicating the size. And you'll see why we have to do that moving forward. Here's an example, and after this slide we'll take a look at a fully coded project that has function calls with arrays. So we start off with a void function named fill_up, and it's declared with an array, an integer array, and a second parameter that's just an integer used to determine the size of the array. And you'll see why. Notice that the array's brackets are empty, so the size is not declared. So then we have an integer array and an integer declared. The integer array's name is score and its size is 5, and the second integer is named number of scores. Then to call fill_up, we pass 2 arguments. The first is just the name, score, just the name of the integer array. And the second argument is number of scores. This is why we need that second argument that quantifies the number of indexed variables stored in the array. Let's take a look at 7.4 now to further clarify this particular concept. Here is a coded example of the void function fill_up that has an integer array as one of its 2 parameters. You can see what this does. Fill_up actually fills the indexed locations in the array with values from the user. And it uses a simple for loop. First it prompts the user to enter whatever size is, numbers. So if it's 10, enter 10 numbers. And then it goes from 0 to less than size. So if it's 10, it will stop at 9. It will stop at 10. It won't process 10. And it takes via cin 10 numbers and assigns them to the index locations in that array. Very common practice to use a for loop to assign values to an array of whatever size. Take a good look at this. Once again, I mentioned this already, but a formal parameter is identified as an array parameter by the brackets with no index expression. That's in the function declaration. But an array argument does not use the brackets. So the call to the function does not require the brackets, just the name of the array. We mentioned earlier that an array parameter acts like a call by reference parameter. An array used as a formal parameter is a placeholder for the argument. Any action performed within the function on the array parameter is performed on the actual array argument. So the values of the index variables can be changed by the function. Thus, the array, when used as a formal parameter or is passed as an argument, acts more like a call by reference parameter than a call by value parameter, obviously. Here, we compare and contrast what a computer knows about an array and what a function knows about an array when it's passed as an argument. Computer knows the base type of the array, the address of the first index variable, and the number of index variables. So it knows the beginning, the quantity of variables, and their size, so it can determine the endpoint. A function, when it receives an array as an argument, only knows the base type and the address of the first index variable. Do you see the problem? Think about this for a second before we move on. Because a function doesn't know the size of an array argument, the programmer should, I would be a little firmer and say must, include a formal parameter that specifies the size of the array. But the function can process arrays of various sizes. A function fill up from 7.4 can easily be used to fill an array of any size, 5, 10, 5 million. But the peril is that if you don't include a formal parameter specifying the size of the array, the function doesn't know it, and the function could easily overwrite data beyond the end of an array when processing with a loop. Think about that for a second. If you don't want a function to be able to change the values of an array argument, you must use the modifier const to make it a constant. An array parameter that includes the const modifier is what's called a constant array parameter. So here's an example of passing an array using the const modifier to the void function show the world, and this way you safeguard against the function being able to change the indexed variables, the values in the indexed variables. If you decide to use const to modify an array parameter, it must be used in the function declaration and the definition. The compiler will issue an error if you write code that changes the value stored in the array parameter, if it's been modified with the const parameter. Here's a cautionary word. If a function with a constant array parameter calls another function using the constant array parameter as an argument, the called function must also use the constant array parameter as a placeholder for the array. The compiler will issue an error if a function is called that does not have a constant array parameter to accept that array argument. This slide shows an example of code that would generate an error message because the second function could change the array parameter, which is a constant array parameter. So take a look at, you've got double compute average, and it takes an integer array and an integer size, and then you've got the function definition for void function named show difference, constant integer array, and a second parameter, integer size. And show difference calls compute average, and it passes A, the array, and compute average does not have a constant modifier, so this will cause an error. Functions cannot return arrays. Later in this class we'll learn how to return a pointer to an array, but right now functions can return ints, double, char, or class type, but they cannot return arrays. Not yet. In the next few slides we'll cover a case study called production graph. Here's the problem definition. We're writing a program for a faux company, Apex Plastic Spoon Company. The program will display a bar graph showing the production of each of 4 plants for a specific week. Each plant has separate records for each department. Input is entered plant by plant, and the output shows 1 asterisk for, and that's the bar graph, for each 1,000 units, and production is rounded to the nearest 1,000 units. We're going to use an array named production to hold total production of each plant. Production for plant N is stored in production N-1. The program must scale production to the nearest 1,000 units to display asterisks in the bar. Using top-down design, we identify 3 subtasks: input data, scale, and graph. Input data will read the input for each plant, set production plant number -1 to the total production for plant number N, and then for each plant we change the index variable to the correct number of asterisks, and last but not least we output the bar graph using the graph function. For this project we'll pass the entire array as an argument for the functions, and we'll also include a formal parameter for the size. The size of the array is equal to the number of plants, and we'll use a constant for the number of plants. Function declaration and main function for the production graph are shown on the next slide, which is 7.5. I strongly suggest you to pull up program 7.5, the code, and load it into the compiler as we move forward in this project. I think I spoke too soon. The code you want is 7.6. 7.5 is an intermediate solution. Actually, not a fully coded solution. It shows the three subtasks and the function declarations for those 3 subtasks. Input void function input data, which passes an integer array, and also an int last plant number, which will be the size. Then you've got scale, which passes an array and the size, and graph, which passes constant int array called asterisk count, and the last plant number will be the size. And there's the very small main program that calls input, scale, and graph, and introduces the program and returns 0. This slide shows the algorithm designed for the function input data. We must read all departments' data for each plant and add them to produce a plant's total. I'm not going to read the rest to you. Take a look at this. We'll have more in the upcoming slides. So we transition from the algorithm to the actual coding in C++, and we're going to use a for loop to step through from plant number 1 to the last plant number, and we will increment the plant number, which is actually the counter. So we'll prompt the user via cout to enter production for plant, and then output the plant number and endl, and then we will get total for for each of the production numbers. So we want to test the function input data. Going back to our previous lectures on testing functions, each function that we're going to have in a program should be tested by a program in which it is the only untested function, because input data calls getTotal, and getTotal is tested first. Once tested, getTotal can be used to test input data. Let's take a closer look. Here we have program 7.6, which is used to test the function input data. And you'll see a dialog on, I believe this is a set of 3 slides depicting all of 7.6. Take a close look at this. You'll see a do while calling input data, production, and number of plants, and it will run through and hopefully not generate any errors. Let's take a look at the second and third slide. Just a quick disclaimer, I find it very difficult, especially in this context, to describe the workings of a program that spans 3 different slides. So I apologize for that. If this were in the classroom, we'd have the entire program in the compiler up on the board via the projector, and we would be troubleshooting this together. But we are stuck with this asynchronous technology, which is good in many ways, but limiting in this particular case. So here we have the second slide, which shows the actual function definition of void function named getTotal. So this is the final, the third of 3 slides testing for the program to test the function of input data. And here we see a sample dialog of a run, and the program prompts us to enter the number of units produced by each department for plant number 1, and to add a negative number to the end of the list, because you can't have negative production. I don't think you can, but in this case you can't. And it simply sums the number of units produced by each department for each plant number, and then it will drop out of the loops and give you the total production for each of plants 1 through 4. I hope you remember the lecture on testing functions. Remember that input data should be tested, and here's some conditions to consider on this project. Input data for a plant, or with a plant that contains no production figures, with a plant having only 1 production figure, with a plant having more than 1 figure, with 0 and non-zero production figures in the same lot. This slide shows the algorithm for the function scale, and it requires 2 parameters, production and number of plants. If you recall, that was a constant. And it changes the value of the indexed variable to show the whole number of asterisks to print. Remember, this is going to print a bar chart, number of asterisks horizontally, and it will divide the value of the indexed variable by 1,000 and round the result to the nearest integer, and that will be the number of asterisks that will be printed for that production number. This slide shows the coding for the function scale. You can see the author's questioning why not use 1,000 instead of 1,000.0. Everyone listening to this lecture, especially at this point in the class, should know why that's done. That's an integer division problem there. In this particular application, we're using a function round called by scale, and it uses the floor function from the CMath library. The floor function returns the first whole number less than its argument. Here's some examples. So it really truncates the any decimal component, and in effect rounds down. If you add 0.5 to the argument for floor, it shows how round performs its task. Before you test scale, you have to test round and make sure that it's fully functional. And then scale should be tested with arguments that are 0, that require a round up, and that require a round down. This slide shows a demonstration program for the function scale. Take a look at this. I hope I still have your attention. I know this is a long case study, but we're, I don't know, 2 or 3 slides away from seeing the final product. And if we look at this in class, we will run the final product in class and demonstrate all of this. So take a look. The next slide will show you, it's slide 2 of 2, will show you a dialogue of this test program and how we accomplish rounding with the floor function by adding 0.5 to the value. So although floor rounds down, so 3.9 gets rounded to 3, 3.7 gets rounded to 3, just as 3.4 would. If you add 0.5 to it, it does accomplish the same as rounding, whereas anything above 3.5 or 3.5 or higher, or 0.5 or higher, will be rounded to the next whole number. So take a look at the values that we used. 2600, 999, 465, and 3501. And they are rounded to 3, 1, 0, and 4 with the function. And that will generate the number of asterisks that will be printed. The complete program to produce the bar graph is found spread over the next 4 slides. As I mentioned earlier, I'm sorry to have to do this, but in this type of presentation, that's how you do. What I would prefer that you do is go to the web study timeline, pull down the code for 7.8, and you'll be able to view the entire code, scroll up and down. And if you are taking a class where it also has an in-class component, in other words, this is not a fully online class, it's a hybrid, we'll be doing this in class. So I'll be going over the next 4 slides briefly, but I really would prefer that you pull down 7.8, download 7.8 from the web study timeline, put it in the compiler in a project, and run it. In this first slide, you see the beginning of the program with the documentation and all of the function declarations. You see the input data function, scale function, graph function, and a function for get total. Many of them are passing arrays of integers, or using integer arrays as parameters, I should say. This slide continues showing you program 7.8. This serves as a reminder. The author's version of 7.8, the CPP file that you have access to with the textbook, does not include all of the code. It uses references to functions that were defined in 7.6 and 7.7. I placed an entire solution with all the code in it, compressed, project compressed, as 7.8, in addition to all the CPP files in the web study timeline. So take a look at that, pull that down, and take a look at the actual final code with all the function definitions included. This slide, the third of 4 slides, shows a sample dialog of the program running before it outputs the graph. So what you probably want to do is vary your numbers when you're running the program so that you get, I don't know, somewhere between 5 and 15,000 as a total for each plant. And that'll give you a nice looking graph, and we'll see the graph for this output, which varies from, looks like 6,000 to 13,800, which will be rounded up to 14,000. And finally, here is the output of that program. Simple bar graph with the plant number and an asterisk for each 1,000 units of production. Rounded up, obviously, with the use of floor and adding 500, or 0.5, I'm sorry, to the units that were scaled down to generate an asterisk for each whole unit. That ends section 7.2. Here is something to contemplate. Can you write a function definition for a function called oneMore, which has a formal parameter for an array of integers and increases the value of each array element by 1? Are other formal parameters needed? Think long and hard about that last question. Do you just need to pass the array as a formal parameter? If you listen to this lecture, you would know the answer is no. And that's all I'm going to say. Think about it.